I'm going to invite to the stage among the biggest brain in the whole industry, the OGs of the OG, the people who've been here for some of them for five years doing VK stuff. So let me just call them one by one. Brian Retford from Risk Zero, Bobbin Threadbare from Polygon Maiden, Jordi Baylina from Polygon Hermes, Zac Williamson from Aztec, Alex Gluchowski from ZK-Sync, and Shahar Papini from StarkWare. To moderate this extremely IQ level, insane, whatever you want to call it, panel where I'm going to ask Federico Carone from Lambda Class, who very courageously took on himself to take the risk. So thank you so much, and have a good time.
Hey, thank you, StarkWare, for organizing this. I'm the dumbest guy in the room, so that's good. I'm going to ask the questions. So, to break the ice, the first question I have, especially for people that have been building ZK-EVMs, is like, what do you believe that will happen when all the EVMs, the ZK-EVMs go to production? Like, what do you think that will happen? Like, we will have many ZK-EVMs. Will they consolidate? What's your idea?
We are going to launch on March.
Anybody else?
I mean, when all come to fruition, I think there is a lot of opportunity to collaborate and do interoperability between these ZK-VM, ZK-EVMs. I mean, if they are all scalable at their core, it shouldn't bring a very hard cost, you know, to interact between all. So I see a place for all of them to coexist. This is my take.
I agree. I think we will see some specialization of the VMs going in different directions with different technical design decisions. For example, like we already see distinctions between ZK-Sync and what Polygon Scroll is building with regard to data availability. Like we use different data availability approaches where some projects put data inputs on the call data in Ethereum. Some projects only put the state delta, final state updates, that give you different properties. So some transactions will be cheaper on one type of system, some will be cheaper on the other one. And there will be more of those changes, which will, I think it's going to be interesting how, like, whether or not and in what direction this specialization will go.
Okay. Is there any other type of specialization that you think that can happen apart from data availability, or like opcodes, or?
Yeah, I guess maybe to. I'm not sure how much new this has, but there's a so in evolution there's a general principle that no two species can occupy the same ecological niche and coexist, because one will outcompete and devour the other. So I think what's going to happen is either that's going to happen, or projects are going to specialize in different niches, basically provide different value propositions through specialization, which I suspect, yeah, I do suspect that's probably what's going to happen, and we'll see them evolve, and yeah, excited to see how things take shape.
Cool. How are you going to manage changes on the EVM? Like, how are you going to keep track of all the changes happening on Ethereum? Like, do you think that's going to be difficult? There has been quite some discussion on Twitter about that.
Yeah, the thing is that at some point, Ethereum is going to be locked. It's going to be fixed. It's going to be finished, if you want. I think that we are still far away on this. You know, sharding needs to be implemented, and we are getting to the final, but it's not. So Ethereum is not final. So thinking in finalizing the roll-up, I think it makes no sense until Ethereum is final somehow. In the while, you need to give some guarantees that what the changes that you are doing, you know, that you are not doing in a malicious way, and that's where you can do these time lock protections, or you can have some specific mechanism for controlling these upgrades in the system in a controlled way. But it's going to be some point, I don't know, maybe in 2, 3, 4, 5 years, that Ethereum is going to be finalized, and then we can think then in finalizing, so not finalizing the roll-ups in the sense that you cannot upgrade unless you're doing some crazy thing.
I think it's one of the great things about roll-ups and layer 2s in general is that you can experiment much faster than at layer 1, where a lot is at stake. So you can go and try different designs and like actually deviate completely from EVM in some senses. So like Kaira is innovating with a different virtual machine and different language. Like we're doing the same at ZK-Sync. We used LLVM compiler, which can compile from Solidity, but also from anything that has LLVM frontend, like Rust or Move. And those features will take it completely away. Like there will be some classes of applications that are not thinkable in Ethereum because the Solidity lacks the expressivity to build those applications in like an efficient manner. Yeah.
Do you want to add anything? No,
not specifically.
Perfect. So this question is more targeted to Brian on Shahar. Like, how was the process of choosing not to go through the EVM like line?
Well, Cairo started as a project for us internally, for StarkWare, to accelerate the development process of our own ZK products. And it didn't really even, okay, it did come up to mind, like maybe do x86 ZK, maybe do EVM, but at the end, the choice was we want the best scaling thing for our products. We don't care internally for compatibility with EVM. We don't even have code for EVM for our product, so we don't need this. So the decision came from there, from our use internally. But I think it also makes sense for StarkNet and for the broader community for cases that don't require Solidity. Maybe if someone is not really locked into his already existing contract in Solidity, where he really wants scaling, so he's prepared to write it in a new framework. And this really suits this use case, in my opinion.
I can repeat it. Like, how was the process of choosing not to go through the EVM route?
Oh, I mean, for us, I think we always just had this thesis that, you know, to really expand the pool of developers in the overall ecosystem, we needed to, you know, give developers more choice in terms of what languages they were using. So that, and, you know, it seemed very crowded. So it was kind of an easy decision to not jump into the fray.
You chose to use the RISC architecture. Did you ever believe that it could be done with x86 or LLVM?
I mean, LLVM is a totally reasonable abstraction point. I think we wanted to use something that actually is sort of reified in silicon. There's like a lot of reasons to do that around sort of the availability of formal verification for RISC-V, as well as like tool variety of tooling and the ability to have binaries run on physical hardware and then also be able to ZK prove the exact same set of instructions. But yeah, anything that level seems like a pretty good abstraction.
And I would say from our side, like within Polygon, like our goal is to extend in Ethereum a number of different ways. So like ZK-EVM is a super important part of this puzzle, but also like Maiden is not a ZK-EVM, it's a different VM, very similar to like Cairo in spirit, not in the actual design. There are a lot of differences, but I think the important part is like, you know, we have one or like several approaches to ZK-EVM, but they also want to provide or cater to other use cases, like to the point earlier, like why, you know, other VMs should exist that can provide functionality that may be difficult or maybe in some ways even impossible to provide with the EVM itself. So like, you know, within Polygon, we're trying to expand Ethereum a number of different ways. Scalability through EVM is one, but also, you know, through different VMs is another approach.
Cool. Do you have any take regarding like if FPGAs or GPUs will be the best thing to use on ZK-EVMs or ZK-EVMs? Like we got the results from the C prize only a few weeks ago. Actually, I believe that MATLabs won some. I don't know if it was the MSM or I don't recall correctly, but some of you are working on that. Do you have any take, like where that will go via FPGAs or CUDA or GPUs?
At least from our side, I think that GPUs are probably going to dominate for at least the next 3 to 5 years, and maybe for much longer than that. It kind of depends on how the use cases evolve. Currently, we see about like a 6 to 10x improvement by using just even your desktop GPU. And we expect to get more like a 50x once we're like finished parallelizing everything for CUDA. I'm actually, personally, I think ZK hardware will show up more in like smaller form factors for like robots and stuff. But I don't know, it's a hot take.
Yeah, here we have some news because we in Polygon we have been investing a lot in FPGAs and GPUs development. Actually, we have very good results from the GPU, especially for speed. So if your goal is to make proofs fast, then GPUs is a good path. But we've seen, for example, if what you are targeting is price, then here GPUs are not as good as we were expected. And let me explain you why. Well, first is because the limitations are not in the computational side. So the bottleneck is not in the computational, it's more in the memory. Right now in our current prover, it takes half a terabyte. So, and this is quite expensive. So adding a GPU is, so you are more cost and you cannot use all the resources in an efficient way. So for prices, so if you're targeting prices, so GPUs is not profitable. And then there is another point that we didn't take in account, and I think it's important, is that, so in the testnet, for example, we are running we have been running at some points like 30 provers in parallel. So here for the price, we're using a lot the spot instances in the cloud services, AWS mainly, but you can have all other clouds. And you know, the market for CPUs is much bigger. So here you have a factor of the cost just by the size of the market that in GPUs you cannot take advantage as good as that. So when you put all the pieces together, we end up to the conclusion that for being cost effective, GPUs, it's currently, with the current proving technology, with the limitations and how we are doing, is not worthy enough if we are targeting prices. If we are targeting latency, it's maybe it could make sense.
I think one thing to make a distinction here is how one intends to use zero-knowledge proofs, because there's two key categories. There's for scaling in privacy. So where scaling is, you're trying to verify computation is performed on, like you're trying to verify with a rather weak computer, computation is being performed on a very powerful computer or a series of computers. And then there's privacy where you care about proving computations over encrypted data. For the latter, which is something that we focus on a lot at Aztec, the available hardware is much more restricted because typically those proofs of knowledge are going to be constructed by the users of whatever system you're building. Typically, if they're going to be consumers, then that's going to be wimpy hardware, phones, old laptops, etc., which restricts what you can use. I mean, at best you can use GPUs, but we're not talking about beefy GPUs in CUDA. We're talking about like Intel integrated GPUs that are not widely supported on the web, for example. And so, yeah, if for privacy-related applications, CPU at the moment is really the best you can get. But certainly for scaling, I do imagine that hardware acceleration will become more and more of a valuable use case, particularly because I feel like Z-Prize was really the first time that the surface had been scratched in terms of optimizing these number theoretic algorithms for dedicated hardware and GPUs. There's still, I feel like there's a lot more work that can be done to squeeze performance out of these devices. But yeah, we'll see for sure.
Yeah, I think fundamentally GPUs are right now, from the architecture, from our experience, they are actually capable of giving you advantage in terms of both cost and latency. But of course, a lot more for latency. So like our implementation is much cheaper on GPUs than on the CPUs, but like latency is a lot smaller. And this is going to be important once we have multiple chains and we have bridges between those chains, and we will actually need really short finality for being able to utilize those bridges, like for great UX for end consumers.
I think one other thing to add is that it also depends on whether you want your prover to run in like available infrastructure on AWS or Azure, or you can build a custom system, because like for FPGAs, for example, there is a limited set of FPGAs that are available in those cloud providers, and you don't even get the best ones. And similar with GPUs. So like if you're able to build your prover on a dedicated hardware, you can take much more advantage of, you know, the specific GPUs or FPGAs. In the cloud, it's not as clear as Jordi said whether it will outcompete CPUs or not. For some proving systems it could, for some setups it could, but not always.
I have another question, changing topics. I know that StarkWare and StarkNet are working on decentralizing the sequencer on the prover. Are you guys working on the same thing, or is there anybody of you that already did some advances on that?
No, I can start. For us at ZK-Sync, it's our top priority. It's our mission to scale Ethereum or like public blockchains in general, and not just for the mass adoption, but like fully preserving the properties that made Ethereum valuable in the first place. And this relies on decentralization to avoid central points of control, to avoid aggregation of power, censorship, and all other things. So we are working hard on decentralizing this sequencer.
Do you believe that at the end, most of those protocols will be the same between each L2, or each one will implement a different protocol? I can explain better. I mean, like, in the space, I'm seeing that a lot of things are converging to the same type of solution. Do you think that will also happen with the sequencer on prover decentralization, or each provider or L2 will have their own solutions?
I think with it we'll see different solutions even within a single ecosystem. Like you're building L3s on top on StarkNet, we're building hyperchains on top of ZK-Sync. Those different chains might choose different decentralization properties. Some of them will be with having centralized sequencers because they don't care. It's a game where validity is the only thing that matters. For some others, they will be broadly decentralized. They will prioritize decentralization over performance. Some others will be somewhere in the middle spot. So we'll have a big variety there.
Yeah, there's no standardization, and there won't be for some time. So we'll see. I mean, I think there are some startups trying, like we want to provide sequencing services, like as a service, and you know, other startups that are trying to that want to provide a kind of an L2 sequencing consensus layer and delegate some of the complexities around at least organizing sequencers. But I think we'll see how that plays out. I think it's far too early to tell. I do have something going back to the original question around like focusing on decentralizing sequencers and provers. I think I agree with probably everyone here that it's very important. I think one risk that I think the L2 space runs the risk of, like, there's a problem that the L2 space runs the risk of falling foul of, which is the potential for infrastructure centralization. For example, I think pretty much all the L2s, ours included, that are in production today, use cloud providers for their provers. And I think it's quite important that the architecture of an L2 is such that your provers can be run on, if not like run-of-the-mill commodity hardware, you can build, individuals can build their own provers and run them without the need for cloud infrastructure providers, because these networks are supposed, well, they need to, like, these networks are permissionless and decentralized, which means you can't control what content is being deployed on them, which means that until the precedent has been firmly established that L2s are networks very much like, you know, the internet, where the content going through fiber optic cables are not, that's not the side of regulation. The regulation is at the site of the application layer. That precedent has not yet been established for Web3 and L2s. And until it does, cloud infrastructure providers are, in my opinion, a rather large potential vulnerability, because if your entire network traffic is flowing through them, then it's very easy for it to be shut down and create like a catastrophic network failure.
Yeah, I totally agree with that, and I think that's one of the reasons, at least, you know, at Risk Zero, we've been really focused on trying to reduce the hardware requirements for the sort of core recursion circuit to be like below 4 gigs of memory, to make sure that as many people as possible can participate, just using their laptop or even their mobile phones in the broader network. And at least from our perspective, that's like part of the reason we're starting from a unsequenced, stateless kind of place, is we want to provide more of an infrastructure layer that is, in fact, far more censorship resistant.
That opens two questions that I have that are related to the things you mentioned. Like the first one is like, did you have any particular security concerns when designing the ZK-EVMs? Like, is there anything different from writing traditional software? What was your experience like? Did you have to like learn during the process? I don't know, like, is there any big difference with writing traditional software, or in terms of security, I mean?
Yeah, I would say that's probably one of the bigger concerns right now, because like if you ask me, let's say 4 or 5 years ago, like what are the biggest issues to be solved in like ZK space, and I would say performance and security, and by now I don't think performance is much of an issue anymore. I mean, there's still a lot of work to be done, but I think it's more or less, we know what needs to be done in performance. On the security level side, I think it's very different from just writing regular software, because you can't create test cases for like missing constraints. It's very, very difficult. You can try to do like formal verification and all of those things, but they are complicated, take time, and you know, bugs can creep up in many different places. So you can do your best, like audit, make sure there is no bugs, make sure it runs in production for a while. But I don't know if there's a silver bullet that exists right now that will say, okay, I have no security concerns. It's kind of like, in a way, and much less so like similar to cryptographic hash functions, where we believe they're secure, but there is really no proof that they're secure. It's kind of nobody has broken them yet.
Do you think that differential fuzzing or formal verification is more important? The two things are complementary, or like, what's your take on that?
I think, I mean, there's a lot of things you can do, and like formal verification is one, but there's other things like audits and all of that. I think all of them need to be done, and more importantly, it needs to run in production, because you know, you verify one part of the system, but are you certain that other part of the system doesn't have bugs and things like that? So it's, you know, it's just battle testedness is one of the important parts of it.
Yeah, I'd agree on that, and also that basically under constraining your algorithm is the largest source of bugs and security vulnerabilities, where you think you're checking like a computation correctly, you think you're checking, like, for example, that an EVM instruction is correctly constrained, but in reality, there's a bug in the software or a bug in the algorithm design, which means that no, that's not strictly the case, and therefore you can create fake proofs with fake inputs. It's a very common problem. As Bobbin said, it's extremely hard to actually like rigorously formally test for. The tooling just isn't there yet. We did find differential fuzzing to be extremely useful, but in small cases, like it's difficult to fuzz like an entire like complicated algorithm that's billions or tens of millions of constraints. But for like basically the equivalent of unit testing for ZK circuits, where you have a relatively small self-contained algorithm doing differential fuzzing to try and find cases where you have inputs that ought not to, for example, satisfy constraints, but your algorithm claims they do. We found that extremely helpful and caught some very, very interesting bugs we would not have found through any other method.
I think security is indeed one of the top things that need to be taken care of, especially at the blockchain world, where so much money is everywhere, and if you make a problem, then all the money goes. In StarkWare, I mean, there are a few places where you can really apply like in a good way, form of verification, I think. I mean, the polynomials is one place where it's a lot more possible, or it's straightforward how a form of verification of something like that could look like, because you have like this set of polynomials, and that's what you need to prove. You can prove statements about them. Doing this about software is a lot harder, like complex software. In StarkWare, we do have this form of verification for the equations, and also for a lot of the library functions we have for Cairo itself. Another important place is the verifier we have on-chain solidity. That is hard to do form verification, but a lot of auditing, I mean, is very important in this space, I think. It's not like form verification or other methods, but auditing is important.
And I would like to add that I also fully agree about security as being the biggest challenge we face with the systems. And I feel that we should be doing audits, we should be doing differential fuzzing, all of the things. At ZK-Sync, we're investing millions of dollars into audits alone, and then the security contests, and then there will be like bug bounties ongoing, etc. But that's not enough. That's like investing in security by construction. Whereas you need orthogonal mechanisms, because like no matter how much you invest in one single mechanism, it can always fail with some remaining probability. Just like you investing in making your ship robust, you still need to have lifeboats and life vests on that ship. That's like a completely orthogonal mechanism that will work even if the original fails. So for ZK rollups, we need something like two-factor authentication, like two-factor protection, where you rely on zero knowledge proofs, but then in addition to that, you rely on something like decentralized consensus mechanism, so that at least two mechanisms need to fail in order for any like severe event to happen. And then on top of that, you can have mitigation strategies, like you monitor the withdrawals, and then you put some limits for some period of time, et cetera, et cetera. So you want to put as many layers of protection rather than just like double downing on one layer and making it as robust as possible.
Yeah, I want to explain us. So mainly in the last 3 months, mainly we have been working very much in the security, and thinking a lot in the security. I want to, in the security we distinguish between 4 possible things that can go wrong, okay? 2 are critical, 2 are, if you want, can be mitigated by the way that we are handling, okay? The ones that are critical, one is, of course, the smart contracts. You can have some bug in the smart contract. Here, of course, we are doing all like any other tap, just audits, bug bounties going on. The cool thing of a smart contracts is that the community is more mature in the smart contract sites, and so you never have, of course, the 100% guarantee that the smart contracts are going to be okay, but it's not the first smart contract that's audited in the space. The other thing is the other thing that can go wrong that would be really bad is what we call the completeness. So if you are proving something that you go to something that's wrong. If the next state, for example, puts a lot of Ether in my account, then that's a critical thing. Okay. For mitigating this, here, besides the auditing and just doing normal checking, here we have an extra thing that's interesting. Is just we are passing all the Ethereum tests because we are all ZK-EVM compatible. That means that we are taking all the Ethereum tests and we are checking that all the Ethereum tests pass. Okay. So this gives us an extra confidence that that the completeness is correct. Again, as a security, 100% security, you never will get it. But I mean, here I feel very comfortable in this part. The other two parts is a soundness mistake. So something that you are here. You can have some mitigation things in the smart contract. For example, if you have 2 provers that prove that the same transactions goes to a different state, then in that case you can halt the smart contracts and maybe going to centralize, and then you have to update on things like that. There is another mitigation is that you can run a trusted prover or centralized prover. At least, of course, you need obligation decentralized prover that they need to prove. So the worst thing is that they don't prove, but there is a timeout, so if this proven, then anybody can prove. But then if you are a trusted prover, that means that you cannot prove something that's not correct, because you are, from the soundness perspective, you can prove. So these are the two protections that the system mitigates. With this soundness, which is probable, I would say, the one that I feel less comfortable, because soundness, proving soundness is where formal verifications make sense, uniqueness, and so on. And here, investment, solid access is as much. So as much as you can is on that. And the last thing that can go wrong is that maybe, especially this is for the forced transactions, but maybe there is some transaction that you cannot prove. That means that the prover gets, then the rollup gets stopped on that. This is the mitigation is very easy, because if you cannot prove, nobody to prove, and then there is just a timeout, and then you just halt, and then you just restart. These are the 4 things. So 2 of them are mitigated, and they're the ones that I'm less comfortable. The 2 that are more critical, I am more comfortable. This is why we are confident to launch, of course, with all the precautions, to mainnet very soon.
Actually, I have a question for you related to that, Shahar. Like, Sierra in some way was designed because of security, or I don't know much about Sierra, to be honest.
Yes, you haven't been to my talk, I assume. Yeah. Yes, Sierra is designed for some kind of security. In a sense, the main purpose is kind of a security for StarkNet, that transactions can't fail and halt the system, or they do a DOS on the system. But the introduction of Sierra actually allows for a lot of safety features on the contract side. For example, users writing contracts on StarkNet can use the strong linear type system that is incorporated in the semantics of StarkNet right now in Sierra to enforce all kinds of invariants and make sure that things don't go crazy. So I think it's a lot of features that help writing secure code on smart contracts.
Perfect. Thank you very much, everyone. I hope we can talk about these things afterwards or tomorrow.